Layout of complex CMOS logic gates. Now we will investigate the problem of constructing a minimum area layout for the complex CMOS logic gate. Figure shows the stick diagram of a first attempt using an arbitrary ordering of the polysilicon gate columns. Note that in this case the separation between polysilicon columns must allow for 1. Diffusion separation, and 2. metal to diffusion contacts in between. This certainly comes a considerable amount of extra silicon area. If we can minimize the number of diffusion area breaks for both NMOS and for PMOS transistor, the separation between polysilicon gate columns can be made smaller, which will reduce the overall horizontal dimension and hence the circuit area and hence the circuit layout area. The number of diffusion breaks can be minimized by changing the ordering of the polysilicon columns. A simple method of finding the optimum ordering gate is Euler path approach. Find a Euler path in the pull-down graph and a Euler path in the pull-up graph with the identical ordering of input labels, that is, find a common Euler path for both graphs. The Euler path is defined as an uninterrupted path that traverses each edge branch of the graph exactly once. Figure shows the construction of a common Euler path for both graphs in our example. Here you can see the figure a complex CMOS logic gate realizing Boolean function. Here you can see the figure stick diagram layout of the complex CMOS logic gate with an arbitrary ordering of the polysilicon gate columns. Here you can see the figure finding a common Euler path in both graphs for N-net and P-net provides a gate ordering that minimizes the number of diffusion breaks and thus minimizes the logic gate layout area. In both cases, the Euler path starts at S and ends at Y. Here you can see in this figure optimized stick diagram layout of the complex CMOS logic gate. It is seen that there is a common sequence E, D, A, B, C in both graphs. At its edge, Euler path for polysilicon gate columns can be arranged according to this sequence, which results in uninterrupted P-type and N-type diffusion areas. The stick diagram of the new layout is shown in figure. In this case, the polysilicon column separation delta D has to allow for only one metal to diffusion contact. The advantages of this new layout are more compact, smaller layout area, simple routing of signals, and consequently less parasitic on capacitance. Here you can see in this figure full CMOS implementation of the XOR function. As a further example of complex CMOS gates, the full CMOS implementation of the exclusive or XOR function is shown in figure. Note that two additional inverters are also needed to obtain the inverse of both input variables A and B. With these inverters, the CMOS XOR circuit in figure requires a total of 12 transistors. Other CMOS realization of the XOR gate that can be implemented with fewer transistors will be examined later. Thank you.